Hey everyone, welcome to another session of Your Desk University. We are really excited that Your Desk University has been able to be so successful over the last year. We have crossed the 1 year mark, and we're grateful to you for your participation in this. We are here to educate and equip people in the AEC community on computational design skills, whether you're a entry-level person who's gone beyond just a little bit of Dynamo, or you're a software developer. We are hoping to educate and equip you, connect you with each other as well. Say hi in the chat. Thank you to all those who are engaging in that way. We also have a Slack channel, and I'll tell you about that in a minute. We're also here to highlight people who are doing things that are cutting edge or revolutionary in our industry, and today's going to be one of those shows. I'm really excited to talk to Leland Curtis in a couple of minutes here, but we are going to be talking about Rhino Grasshopper. We're going to be talking about hops, some of their new technology that allows Grasshopper to connect with Python 3, and machine learning. Now, I don't use the term machine learning very lightly. I personally have pushed off quite a few sessions where people wanted to talk about machine learning because I felt like the sessions were just not quite there. Maybe they were just talking about, checking numbers or looking at naming conventions or something that just didn't feel like it gave that, what I'm going to call buzzword, really the meat for it. And so I've kept this, and when Leland Curtis and I talked about this, I thought this is great. And it's also going to pair really nicely with next week's session, which you can see. Definitely go there, hit the subscribe, hit the bell so you get the notification when the new sessions come up. But Chris Mackey is going to be with us next week, and he's going to be talking about the infrastructure, not infrastructure like bridges and all that, but infrastructure behind coding and what does it take to create an ecosystem that can create software for sustainability. I'm really excited to hear about that, and that's obviously with regards to Ladybug and all the stuff that they're doing, and that's really been pushing our industry a lot as well. So with that, I won't take any more of your time. I'll introduce Leland. He's on the camera now. I think, yep, you're this way. I always have to remember which way to look. Leland works at Smith Group. He's a co-lead of computational design there. Smith Group, if you don't know them, is about a 1,300 person architectural firm. I've been pretty engaged with them here in the DC area, but I think you're in Detroit, Chicago, Denver. Moved around between those maybe. And with that, let's first just talk a little bit about what we're going to talk about before we get going with the presentation. So Leland, can you give us like a quick 20-second?
Yeah, effectively, I totally agree with you with the buzzword around machine learning. It's kind of meaningless. And I see machine learning as just a collection of tools that are native to the information age. And I've been really passionate about trying to figure out how to actually apply this. I'm hoping today in discussing surrogate modeling, identifying what that is and how it can take any parametric model you have and turn it into a real-time predictive model that allows you, it gives you a map of your design problem. So I'm going to showcase not only how to build surrogate models, but also talk about how I think they can be best applied to really transform sustainable design.
Because the analysis you're doing just takes too much time to be iterating when we're talking about like 10 seconds or 3 minutes or trying to do like multiple options really quickly. Doing a full analysis just isn't feasible. Is that right?
Exactly, and it's also not flexible enough. As we'll get into this presentation, I think the paradigm of optioneering, of testing or choosing between 4 preconceived options, isn't good enough to meet the 2030 challenge. And so to do better, we need to really rip out our whole concept of how we perform sustainable design analysis, from option testing, validating options, to some stuff that's supported by workflows like I'm going to show here today that can really just supercharge the design process with information in ways that our current toolkit can't.
Yeah, I'm definitely excited to hear about that, and definitely keep engaging with us in the chat. I will be watching that for questions. So if you have a question, if something comes up and you want to know more about it, that's the place to put it. Leland, you're also watching the chat on your end while he's presenting, doing 2 things at once. So with that, let's dig in. Let's learn a little bit about this, and I will be interrupting him. So if you guys want to challenge him, again, I think when I posted about this on Twitter and on LinkedIn, I said, that's a ton of buzzwords. So My question to you is: are we really giving it its weight? So I know, Leland, I'm really putting the pressure here,
Oh man.
but I know that you can. I know you can deliver. So I'm really excited. Let's dig in.
Yeah, and please interrupt. I hope this can be a conversation. I'm just really grateful to have a platform. I can even see people on the chat here. I look forward to getting these ideas out in front of others who are thinking the same way. We often run into this problem, I think, where we're all alone in the dark, kind of, especially a field like ours that's small but spread out. Uh, I hope others are working on these ideas. So please speak up if you've got a better version of what I'm showing. The point of presenting this is to try to collect these ideas and get them out there under the light. So yeah, please interrupt throughout this and add comments. Everyone watching, I really want to know what you think.
All right, practical machine learning. I'm
Yeah,
watching. I've got it
let's
displayed now.
let's do it. Hi everyone. I'm Leland Curtis, co-lead of computational design within our technology and practice group, and this talk is going to be colored by the role that Smith Group plays, I think, in the industry. So Smith Group is a large architectural engineering firm. So we have a lot of designers, but we also have all of the in-house experts of a multidisciplinary integrated firm. And so much of what I'm going to be showing today is looking at the challenge of sustainable design through the lens of a firm like Smith Group, where our goal, and really where I live, is at the nexus of engineering and design. So how can we inform the design process? We have an advantage at Smith Group in that I'm not a consultant on the outside. I can directly, through Teams, call up our lead designers and have a conversation with them. So I'm really looking for ways to get our analysis into the design process to support the designers, to encourage design freedom, but to make sure that we are meeting our 2030 commitments, that we are really understanding the impacts of our design decisions. And so that's what I'll be talking about today. So this is the overview of the workflow that we'll be going through. By the end, I hope the term surrogate modeling doesn't sound like something weird and somehow related to pregnancy, because it's not. The workflow here, talking about taking a parametric model in Grasshopper, generating a bunch of data using something like Calibri, and then spitting it out of Grasshopper into a proper coding platform. So in this case, I'll be using Jupyter Notebooks to clean the data, and then TensorFlow and Keras to train a surrogate modeling. This is the machine learning part of it. And then bringing it back into Grasshopper to deploy it in actual relevant design workflows using hops, and we'll also talk about the OWL plugin. So I don't expect you to remember any of that. We'll go through it. But to explain surrogate modeling, I really need to rewind the tape a little bit and talk about the main flaws that I see in our current process and give an overview of design space thinking, because all of this stems from design space thinking. Exactly. And that's what's so exciting, is that I think this is a very generic workflow, and surrogate modeling in general is one subset of machine learning. It's it's the simplest, one of the simplest forms, and can be applied in any number of ways. I came from daylighting, so I'm an architectural engineer by trade. Started out as a lighting designer. Actually got into Grasshopper through Ladybug. I'm super excited that Chris Mackey's joining next week. They are all stars. And so all of this is through the lens of my needs. But I hope that the workflow I'm sharing today, you all watching can see, oh, I can apply that to my own problems. Yeah, it was a great point to make. So the fundamental challenge that I face, that I was trying to solve, is my frustration with performance analysis in general. It strikes me that there's a fundamental flaw in that and it just comes down to any analysis. In order to analyze a design, we need a design to analyze, which means by the time we get the information, it's too late. The decisions have already been made. The design already exists. By the very nature, we lag the design process. So if our goal is to inform design, we're starting behind the eight ball. Like, no matter how fast your tool is, it's always too slow and too late. But we can do better. So if you take a step back and say, all right, anything is possible, right? I'm an optimist. Anyone who's ever talked to me, right? I got my head in the clouds. But in an ideal world, if anything were possible, we would want to have information and analysis and an understanding of our problem before we make a design decision, or certainly while we're making design decisions, not after the fact, not 2 weeks, not 2 days, not 2 hours. While we're designing, we want to know. And that is now possible, and that's what surrogate modeling promises to deliver. And I like to look at this through the lens of this data pyramid. For those of you who've seen this, it basically makes the case that there are higher order products based on data and information. And all of our current tools, I believe, are delivering information. So right, data would be like a number, 42, meaningless and useless. But as soon as you say, oh, your EUI is 42, that's information. And as you add more context and more meaning, you kind of move up this data pyramid. So all of our current simulation engines are effectively set up to analyze design options, right? To take a design and output a number. Here's how you did. And as soon as you get that number, your tool stops there. So here's how you did. Well, how do you do better? Why did I do this well or this poorly? What if I did these things? And from the immediate next question, our tools have failed us. And we rely on rules of thumb, experience, and it's our experts who are interpreting all of this. And that's why a company like Smith Group has experts in house, because we rely on that. But what I propose is that we need tools that can deliver higher order products, that can deliver knowledge and wisdom. And that's where these fancy buzzwords of machine learning, and all this, they can help break the mold and break us out of this limited paradigm that we're in. And so through that lens, I like to say, all right, to bring this to an analogy of the design process. So think of the design process as being like lost in the woods, where you have a design team, you got your architect, you got your engineers, whatever, you're all in the woods, you're trying to get out. Our current process is like blindly stumbling through the woods, or you have several paths. Which one gets you out? Let's send a runner down different paths. They come back and say yes or no, but you don't really have a good understanding of where you are. In this analogy, what we really need is a map. Because if we had a map and someone who could read that map, we could simply say, hey, not only where am I, but how do I get out? How do I get out fastest? How do I get out without climbing a mountain, right? We want to understand our problem. We want a map of our problem. That's what a surrogate is. A surrogate model is a map of your design challenge that delivers more detailed and more complete understanding, right? Going back to this pyramid, knowledge, wisdom, and understanding of your problem. That's what a map is. That's what a surrogate is. And to explain that, I got to now explain design space. So this gets a bit weird. I made some visual examples to try to make this more visual. I'm a visual thinker, so I hope this makes sense to you. This is our current paradigm. A parametric model is a design space. But if we think about it this way, we're missing the potential. So here's a parametric model where as I adjust my parameters, you see the facade changing. But I'm still looking at a single thing that's dynamic. But really, the parametric model is every single frame of this video. Every possibility contained within that parametric model is part of it. But so we need to break out of looking at it as a singular object. So instead, let's consider it as a design space. So let's unroll all those possibilities. So let's adjust it by window width. Okay, I have this collection of design options. Try a different parameter, fin depth. I now have an array of possibilities. Add a third dimension here, a third parameter, and now you'll see I have a space of design possibilities. This is my design space. And now don't look at these as actual options. Consider them as data points defined by their coordinates within that design space. So I know that got a little weird, but what I just showed you here is that you can translate any parametric model of any physical design challenge you have, you can translate that into data. And as soon as your design problem has been represented as data, that opens the world of analytics, algorithms, and the information age, right? And surrogates in that context are basically they're function approximators. They are the best fit line. So all of us have used Excel. We have a scatter plot, and you do a best fit line through. Is it a straight line? Is it a polynomial? Right? You just kind of get that best fit line through your data. Well, as I just described, if every data point is an actual design, take this case, options A, B, and C over here. Well, the parametric model is more than just those three. It's every possibility between those three. It's the best fit line. And so if I have option D, I know it's somewhere between A and B. Now my parametric model might allow me to go to option D. What a surrogate does is it takes those few options and it then mathematically creates that best fit line. So it becomes the parametric model to then say, what's option D? It'll just predict it, because just like a best fit line will tell you what that value is. And what's key about this, looking at this diagram, surrogates replace your parametric engine. So if option A at the top here, step one is to build a parametric script. This is especially useful for slow simulation workflows. So let's say it's an energy model or a daylighting analysis that takes 5 minutes, 5 hours. That's option A. So it takes 5 hours from these inputs. Here's my output. Well, let's say you run it on the cloud. You run it on 10 machines. You run it over the weekend, right? You now have a lot of inputs and their corresponding outputs. And machine learning will learn from that combination, that data of inputs and outputs. It'll learn all the patterns so that in step C, given any new input, it'll predict an output. Because that machine learning process is the generation of the best fit line. So once I have that, I can instantly predict any value. Notice step C and step A are basically the same. I've just simply replaced all that parametric scripting with a predictive engine. That's surrogate modeling. And that means we can replace slow simulation engines with instantaneous real-time predictors, real-time surrogates, or maps of our design problem. So let's look at this in practice, because this isn't just theory. Like, we are using this. So I came from the daylighting world, and it's a slow analysis to run. So here is a prototype app. This is using Grasshopper and Human UI. And as I adjust this parametric facade, you notice that I'm getting real-time feedback on the effect of the interior daylight. And this is detailed stuff. I'm looking at shade triggers, and more than just how well is one option doing. Here's a design space of 1,000 simulations that's getting predicted in real time, because that's how fast the surrogate is. So as I filter down my design space, I can then also understand how my current idea, not only how is it doing, but where does it fit within the range of possibilities? How does any single decision affect the performance? My goal is not to say how am I doing, but how could I do? So here's real-time sensitivity analysis telling me mathematically which parameter has the greatest impact. And then as I adjust the region that I'm looking at, that's going to change depending on the region of the space that I'm in. So this is, I know that was a quick video, but it's just making the case that once you have a surrogate, you can get lots of information. You don't have to work in the same way you did in the past. You no longer have to test a few options. You can use this to interrogate your challenge, to understand your design problem in more detail. And so now our challenge is, okay, this is possible. Well, how are we integrating this into the design process? So that exact same surrogate engine, we've simply applied it in a new way to make it more visual, maybe more useful to our designers. So here, this is not even really sped up that much. You see a Grasshopper script that's slicing any massing and saying, how good is your daylighting going to be? But notice that this is a realistic facade with shade control, with all these other decisions that I know affect daylighting performance. So the days of just having a really simplified model to get it fast enough are over. Here I have incredibly detailed analysis delivered in real time in a format that can make sense and guide me towards a better decision. But what's wild about this, and this is a prototype, right? I wouldn't even call this a real piece of design software. Imagine the possibilities if we can now get our hands on this kind of information, where in the old days, you would pay somebody like me to take your massing and run a daylighting analysis, and 8 hours later, deliver some pretty meaningless information that's barely better than your rule of thumb. That's not good enough. Imagine instead you had a design app that delivered real understanding and insight into your design process. So showing this, what I'm saying is that I think engineers and performance analysts will cease to be tool technicians that are experts at running simulation software, and instead will end up designing these apps that inform the process in new ways. And I think surrogate modeling, as shown here, really opened the door to a new generation of informed design tools.
So to unfold a little bit of what you're doing here, what are your key features when you're looking at what we're looking at on the screen?
Well, the big things I would say, it's all about the parameters, the design decisions.
Mm-hmm.
What are the design decisions that I have to make? What are the ranges? So some of them, I would call them filters, where what's the location? That's set by the project, right? What's the context like? And so some of these things I can set. Other things would be more flexible, like, do I want a sill height or not? Generally, how much glass do I have? Do I have program right up against the windows, or is it really far off? Those are decisions I have to make, and I don't know which of those in what combination has what impact. It's a really complicated problem, right? It's not one dimensional, even 2 dimensions. I have 10 different parameters I can play
visualize that in 3D.
You know what? You don't even have time to play or to explore all 10 options. It's a complicated problem.
And then you're looking at like different points along the surface as they're distanced back in order to get the information about that particular part of the mesh or something.
Yeah, and so I don't want to go into too many details with this. And this actually, if seeing what we have now, I would have collected the data this is built on in a different way. So what this is
Of
actually
course.
measuring is each of these lines here is, it's probably hard to read, daylight autonomy at different levels. So DA 300 is
Mhm.
what leads based on, your SDA is based on. So if you look at everything yellow and up, that's saying, I think we can get above 50% DA 300, this depth into the space, depending on the parameters of this facade. And this is really simplified. I'm kind of just rounding the corner. So I'm taking a measurement at each facade in different ways, just to kind of estimate based on real hard data. And then as you go back the different colors, it's a different threshold.
And so by
But
building these
yeah.
surrogate models, what's the downside? Because obviously you're getting this performance, but if it was definitely like if it was always solving the same problem in the same way that the analysis was, then obviously like what's our loss? Is it accuracy? Is we're gaining kind of a general idea, but we're introducing some other issue?
It's a great
And
question.
maybe we'll get into that, and maybe we can just keep going. But I think
Actually,
it's important as we kind of like
I think I'm
touch on
about to
this.
get into it. The major things I see, there's certain applications that are really well suited for this, and others that are not. One of the main problems that we find is, I'll call it, if it's generalizable or not. Many of our designs are truly unique, and you'd want to. There's no need to run a surrogate on that because it's all about sort of predicting between sort of things that you've learned. And as we get better and better, I think our surrogates will become more and more applicable to more general problems. And there's a whole field of study on how to do that. And this process I'm showing you, where you very clearly defined parameters, what it's saying is that within that design space, it's going to work pretty well, very well. If you're outside of that design space, it's not. That's a major limitation. So there's a real art in the framing of the design space.
Because you understand the algorithm, you understand your data set within your space, but then once it goes out, is how does it interpolate into space that you have never explored yet?
Exactly, and
Cool.
I would say it's not applicable in that way. But there's some things that we've stumbled into. This is sort of a sidetrack, but what I'm showing with these very structured design spaces, they are inherently interpretable, meaning that the data is structured and the surrogate is built around these key design decisions. So when I showed that example with the the sensitivity analysis, it was in terms of the parameters because that's how the data was structured. So I can run that analysis to say this decision means this much. That's fundamentally different from other methods, which are more about I would call them like real-time simulators that are really generalizable. So Theodore, people on this call have probably seen some of his amazing work. I follow him on LinkedIn. If you don't, you all should. He's had some amazing full floor plate daylight calculators, which I think are far better than this as far as really understanding the nuance. But they don't explain where. It's a little more black box. It'll deliver an answer, but it's not going to project out to the edges of the woods in my analogy. So I'm kind of have this internal conflict of, I see two different approaches. One is to simulate anything you might see immediately. That's like a real-time engine. And then these design space surrogates that I'm working on are more about interpreting the larger problem, because I want to have a flashlight ahead of the design team. And I'm hopeful that this process is going to give
it can kind of
less
guide them,
information.
like kind of go this direction,
Yeah.
kind of go this direction. And I do want to be careful
both
how
are
long we
good.
take on this question, because I know you have code later for people to look at. And I know the people who watch this and who are still with us or who are just joining in because they got the alert, they really want to get into, wait, I could do this too. And so let's keep going.
Yeah.
I just want to be careful on, love it.
It's a great questions though, and I want to give a shout out to Dr. Richard Mistrick. He joined us on sabbatical a couple years ago, and he helped develop the design space, all that data that I'm going to be getting into in a minute here. So a big shout out to Rick. Without his work, we wouldn't be able to be talking about what we're talking about today. So sort of in review of the surrogate modeling workflow, if you can parametrically model your problem, you can work this way. And I think the key applications are those where you want to model your design decisions, where you're you have certain decisions to make, but you're unsure about how they all relate. That seems to be the best case for these surrogates. So you model it parametrically, you then simulate all your iterations. And for performance analysis, this is where Ladybug tools would come in, because that's these first two steps. Once you have all your data generated, then you train your surrogate. And once you have that surrogate, you are now able to inform design in new ways. So that's the general workflow that we're talking about here. As far as applications, I think kind of goes right along with the question you just had there. I think this approach is most useful in what I call a universal design space. So I've deployed this methodology on actual projects where I kind of know where the design team's going. They haven't come to a design yet, and I'll simulate a whole bunch of different facades, let's say. And then we sit down at a meeting and we're able to play and explore that unique problem. But I still had to turn that around in several days. So I'm still kind of lagging behind the design process. But if it's a universal problem, a common problem, imagine for a second, if we have the same problems over and over and over again, and we're constantly re-simulating them because it's slightly different, what if we could simulate enough data to map that problem? Because if you have it, that means, in theory, you could have instantaneous, great analysis on every project for free because it's done. And there are a lot of problems that we could do it this way. I'm not saying every problem, but some. This is the low-hanging fruit. So what you saw with that design space of the daylighting, that's a pretty common problem that can be applied to just about everything. And so a lot of my work now is focusing on that. But I'm curious what people on the call think about good applications. But I do think that the universal design space, you might even take a month simulating all the data, but then it's done forever and for every project. And honestly, for the entire industry.
And by the call, he means you on YouTube. So put those comments either down below if you're watching this after or in the chat over next to us, because we definitely want to get your input as we're going along.
Let's get into the details, right? Let's start seeing some of the code. So what I've just shown so far kind of covered some of the parametric modeling and the generating of the data. Just shout out Calibri is my favorite iterator. There's a whole nother presentation about how best to simulate, but we'll skip that. So if we're talking about universal design spaces in particular, these require a lot of data. And actually trying to bring in that daylighting design space that you saw those tools built on, it broke Grasshopper. It couldn't even import that amount of data. 62,000 rows, 24 columns. Grasshopper's slow. It's not the best way to do that. And I really think that if we're doing anything really cool with these new algorithms, we're going to need a lot of data, and it can't be done in Grasshopper. So that means we need to find a way to train up our models outside of Grasshopper and then bring them back in. So I've been using Jupyter Notebooks for the data cleanup process, as well as TensorFlow and Keras to train the surrogates. So let's dive into that. For those of you who haven't used Jupyter Notebooks, I'm not a coding guy originally, and I really like Jupyter Notebooks because they're very visual. So as you see here in the screen, some of the lines are actually, you write text. It reads like a notebook that has code inside. And data scientists in the real world use this all the time because you're able to very quickly interrogate your data, make plots, scatter plots, test different things. And effectively think of this as it's like Excel, but even opening 62,000. Here you can see this line right here. So I'm using NumPy, Pandas, Matplotlib, and Seaborn for different plots, and sklearn for all these different fancy features. So if I were to try to do all this data work in Excel, it would be impossible to open. It'd be slow to use. It's just not the right way. No one who really does this does it in that way, not when you're dealing with lots of data. So here's just a couple examples where a couple lines of code, I import my raw data. I'm able to say, hey, what's the total shape? 62,000 rows, 24 columns. Here's one command where I'm able to identify what's the total number of unique inputs that I have in my entire data set. So if you have perfect data, you might not need to do this. You nearly always will not, right? That's kind of the real world. So you need to wrangle your data. You need to make sure that you don't have nulls. Like, is it wrong? In going through this thing, like, why do I have 3 locations? I only simulated 2. There's a problem. Let's go fix it. And good luck finding that problem in 62,000 rows. You need code. Therefore, you need something like Jupyter. So we go through here, and this is just showing some of the examples of things that we might do. I'm able, with one command, identify all of the columns as I start to slice and dice my data set into different chunks, in this case, into the input parameters and the output metrics. So all of this is done in code. And here's one line, x.describe, where I'm running an analysis of all of the data to get a sense of, hey, what's the mean, the minimum, the max, the 75th percentile. This starts to give me a lot of information about the quality of and structure of my data. So all of this data science is critical to any kind of machine learning, because garbage in, garbage out, and it's very important to do this. I actually went back to sort of like night school. I took a Udacity nano degree on data science, found it really, really useful because this underpins all of the machine learning stuff that we'll be talking about. So let's assume now that all of our data is clean, it's ready to go. To actually train up a surrogate, first you want to scale your data. You don't want the algorithm to overweight one value versus another. For example, my windowsill between 1 and 2.5 feet, and my orientation is between 0 and 360 degrees. I don't want that to affect anything. I want them all to be between 0 and 1. So using a little bit of sklearn, they've all been scaled. And you see here at the bottom, a little command. I look at it to confirm it worked properly. So Jupyter Notebooks is great for this kind of thing. So everything looks good. You then want to split into testing and training. The way that the machine learning algorithms work, they're kind of an optimizing process. So you have a chunk of your data that it learns from, but in order to say whether it's right or wrong, you need to have some testing information to create a loss function, almost like the fitness function from Galapagos. Like, is it good or bad? And that kind of guides the process as it learns. So we use some functions to split it into training and testing. And then building the surrogate is probably the easiest part. Using TensorFlow and Keras in particular, a couple lines of code. So here in chunk 52, I'm defining the architecture of my neural network. In this case, I use a pretty shallow neural network as a regressor. And if you want to learn more about the types of machine learning, again, it could take all years and years to talk about it. But in general, I know that I want to have that best fit line. That is a regressor. We're not talking about classification or dimensionality reduction or any of that weird stuff. I just need a regressor. There's a bunch of different algorithm types. Neural networks can work as regressors. And I like TensorFlow because it gives us lots of options. So as you get into this, you'll notice I'm using a sigmoid activation function. That's pretty standard. If I wanted a ReLU, I don't believe that you can access ReLU activation functions within, say, accord.net, which you might be able to access natively in Grasshopper. That's what OWL and some of these other components are built on. So being able to work in Python 3.0, which TensorFlow is in, gives you access to the latest and greatest world of machine learning, which is why it's so critical that we get out of Grasshopper and get into the world where the rest of machine learning is happening, so that we can build complicated, proper algorithm types.
So before the
yeah.
hops was available, you were using the Grasshopper, OWL, the .NET,
Yep.
in order to access your machine and then get the results?
Exactly. And I got a couple slides on how we went around that before we jump into hops.
Cool.
Yep. So in TensorFlow here, we design the model, and then you compile it. And here I just want to point out that there's also advanced features like exactly what kind of optimizer are you using, what kind of loss functions. And there's no easy way of identifying the best version of this. And I've always been frustrated trying to learn more about machine learning. It's like, well, why do this architecture? Why not a different one? I found great success in very shallow networks, one dense layer with 500 nodes compared to this structure. Depends on your data, and no one has a good answer on what works or what doesn't. And that's why it's an entire field of machine learning engineering on figuring out how to do this. And there's tons in here. So big point is TensorFlow and Keras makes it easy to build, and there's lots of advanced features that you gotta have access to, which are necessary to do anything that's unique and works for your unique data set. And then training it, you just feed it in all the data, and it can run. This cannot be done in Grasshopper because Grasshopper is not well optimized for this kind of data. But all of these NumPy, TensorFlow, it's all designed for big data analytics. So this can run very easily on my laptop. And then you can save the model. You can load a new model, right? If you can get access to TensorFlow and Keras, you're good to go. But you can't. And then just want to point out as far as the values go, quite good accuracy. And I actually think that we still have some issues in the underlying data, but even here at the 75th percentile, you'll see that this is the mean error. So if 0 to 100 or 0 to 1 is the SDA, 0 to 100%, my error at the 75th percentile is 2% or less. That means that nearly all these values are right on line with the predictions. And actually, if we look at this plotted, you'll see here, this is training it on 80% of the data. Nearly all of these values are right on the line. Almost all of them certainly within 5%. And these here are like a single value of 62,000. So even these faded parts are almost negligent in the space. And what's really exciting to me, maybe I'm just too much of a nerd here, but the exact same setup. Perfect. But if you train this on 5% of your data, 5%, this looks a lot worse, but almost every value is within 5% here. So this first line's 5, the second line's 10. And yeah, you've got some more error at the edges here, but For only 5%, this is remarkable performance. And what this tells me
Mhm.
is that I think there's a potential, especially in the drive for a universal design space that's as large as possible, because machine learning is not, these surrogates aren't predicting between, say, here's two simulations I tested, measure halfway between them. That's not what it's doing. It's learning the patterns, and it's able to project that best fit line or that hyperspace plane into unseen regions of the design space, which means a few samples, especially if they're collected in an intelligent way, will allow us to simulate through a surrogate a much larger design space. So I think there's a huge potential to really generate very, very large design spaces without the burden of simulating every aspect of the space. All right, so that's getting into, so again, using
So
Jupyter.
using Grasshopper, I think you were a little. At least I was confused in the way you
Mhm.
worded it. You are using Grasshopper right now in order to run all of your data sets with
Yes.
Grasshopper and Calibri, and then you're using this in order to train and evaluate all your data sets.
Correct. The data is generated through a Grasshopper. But actually, I think it'd be cool. You have Chris Mackey coming on next week with Ladybug tools. Um, if you think about it, if if I'm using Grasshopper to set up my design problem and my physical geometry, and let's say I'm using
Mm-hmm.
Ladybug to actually run the data linked analysis, that data linked analysis is being run elsewhere. It's just being sort of packaged or triggered through Grasshopper. And the way that Ladybug tools is now set up, where you can sort of batch generate all of your simulations, it's kind of getting even weirder than that. And I really look forward to next week's presentation. But the idea is, yeah, use Grasshopper to define your design space, your parametric model. Generate all the data that you need through that. Once the data is collected, open that up in Jupyter to clean it, wrangle it, and train your actual model.
Mm-hmm.
And now we're at the fun part. Let's deploy it. So before we jump into hops, which is the way we would recommend, I want to talk about the way we used to have to do it, because I think this is important. And I want to give a shout out to Matthew Bro from Handle Architects, computational design lead out there. This guy is great if you guys haven't met him. He and I met at a TT hackathon a while ago, and we've been kind of meeting nights and weekends talking about these ideas ever since we kind of failed at this a while ago at one of our hack projects. And so he's been really instrumental in developing some of these ideas. So even though I'm presenting them, this is a joint effort. Really want to give a shout out to Matthew. So one of the things that we stumbled into, so we knew that we could train up small data sets, 100 to 1,000 samples or so in Grasshopper, and I still use that for some of my tools if they're small enough. But to do anything real, and certainly with this data set from Dr. Mistrick, it just straight up wouldn't work. So we needed a way to bring in a model trained outside to bring it in. And without getting too much into the weeds, to run within Grasshopper, it needs to be something through IronPython. It needs to be .NET. So you can't have access to Keras or TensorFlow. And there are some machine learning packages that are accessible, in particular Accord.NET. So OWL is one of my favorite machine learning packages. They've effectively just packaged up all the Accord.NET machine learning tools into nice Grasshopper components. You're still limited by Grasshopper's ability to actually train it, but you at least have access to the code. And they have a cool component, which is really nice. This one here on the right, this train network, you're able to assign weights and biases to a pre-constructed network. It's almost like initializing the values. In the end of the day, the neural net is just a simple matrix of numbers that it takes a ton of work to optimize all the weights. But once that's been done, this is allowing you to effectively import the weights and biases as from a CSV file and then simply apply them to the network. And this only works if you're if you're constructing a network that OWL lets you build. So we don't have access to ReLU functions. We don't have access to certain complex structures. But if it's a simple structure, we can build it as a basic network in Grasshopper. And then by importing all the weights here, setting them up in the right tensors, you can just apply it. So this is actually how I've been deploying these tools. So that daylighting one that you saw is using this structure. And this is actually what I'd intended to share with everybody today. But then I think like a few weeks before now, Hops comes out, which is, I am so excited. If there's any Rhino people out here, oh, like I hate all this
And they
.NET.
are
Oh
watching.
man, you guys are the
So
best. You guys are the best. I was so
definitely.
frustrated by not being able to access the libraries I wanted, right? Being limited to Python, Iron Python, Python 2.7. And also I don't like that stuff. All that comp sci things, I'm trying to get better, but man, it's hard. So Hops is great because it's giving me the ability to access anything that I want. So now I'm going to walk you through the hops version of our surrogate model. I don't want to get into too many details here because if you really want to learn this, this link that I have at the top here, there are tutorial videos out there that you should watch. So I'm not trying to replace those. I just simply want to say, all right, having followed this, they have a template for how to spin up the Flask server and get a hops component going. So just showing you how I applied it to the surrogate modeling problem. This first slide here, I am, just like in C# programming of a custom Grasshopper component, I'm defining all of my inputs and my outputs, right, to make my component. And then what's really cool is that within here, I get to scale my all of the inputs. You know, that process, I need to scale it down to 0 and 1. Well, in Grasshopper, this is slow. And a lot of my programs I've been working on, this is what bogs them down and makes them not as fast as I'd like. So being able to spit that out and use NumPy to do it, it's like, hell yeah. This is really good. This is really good.
Yeah, take advantage of something that already does a lot of the work for you.
Yeah. It's something we ran into, Matthew and I, in working through this. The machine learning algorithms they kind of expect an array of inputs. So just a little trick here for anyone watching, using this, changing the shape. So creating a new array, so as the inputs come in, I guess it's seen as one column of, say, 10 rows of one column. That's like the array. And what the machine learning algorithm expects is one row of 10 columns. So you kind of need to flip that. So heads up, it took us a little bit to figure out what was going wrong there. So this little bit here, just to change the array shape. And then you just load the model with like a line, k.models.load model. There's the path. Bam, I have it. And I can start to predict. In order for this to work properly, it's important to load the model outside of the definition that gets called by the component every time. So put it down here by the app.run part. This way it loads it up once. And we added another bit that would call that model, the Keras model, as a global variable. And this means that you can use it for predictions without having to reload it every time. If anyone's looking to follow along, that was a nice trick that allowed it to be real time. And we added a little check so that if you add a new, say, surrogate model path to load up a different model, it checks, loads it, and then once it's been loaded, it's good to go. But again, putting the model outside of the loop and then calling it as a global variable is helpful. And here you go. All of this so that I can run this line, predictions, model.predict, bam. And it predicts it and I return it. So here's what it looks like. Here's a little video. Here's the Grasshopper node with my 10 inputs. And as I change it, you see in the terminal here that Flask server is running this. As I update the model, the next time I run a simulation takes about a second. And then from there, it's down to like 50 milliseconds. So it works. The next steps here are because again, this just came out. We just had time to check it out to make sure we want to.
Hops is really nice, but obviously, the way you had been doing it had been working pretty well.
It worked, but moving forward, this I think is the way to go. It also allows you to develop in the right format without limitation, and I think it's going to be much more portable. So I see hops more as the idea of, especially with these surrogates, like build them elsewhere, deploy them in any number of ways. A standalone web application, sure, go for it. Build it in one spot. And I see hops as simply a way of getting it into the design process through almost like a custom design app that leverages all of this power that could be taken from the outside world.
And I think that's actually a really important piece, because I almost wanted to interject earlier when you were talking about like different models and different spaces and how you're evaluating, right? Machine learning is kind of a field of statistics and data science, and statistics is a massive, massive field. And so for us to think that I'll be generous, in a few months that we can become experts on statistics, let alone, I'm not pointing out to you, but just like, let alone people think that we can do it in like 3 days. Oh yeah, I did Dynamo and Grasshopper for 5 minutes. Now I'm an expert on machine learning. And I think that that's really dangerous. But I think what you're talking about here is the machines can be trained and set up, and then people can access them from all over the place. And I think that's really powerful, and the way we're looking at doing that too.
Absolutely. And actually, one of the main reasons I wanted to talk about this is that I think that there's an opportunity for the industry to not compete on these. First of all, in order for us to learn this, do you have to be the machine learning expert to design the surrogate model design app, or do you simply need access to a good surrogate? Because I want to learn from you all, right? I want to see what everyone else comes up with so I can develop better versions myself, right? Let's all, let's not compete over who has the best Excel spreadsheet. Let's not compete over who has the best sidelit daylighting surrogate, right? There's a lot of things you can do. Actually, Mackey, I heard him present at a conference. He talked about let's not compete on the trunk. Let's compete at the branches, but let's build the trunk together. Especially with a lot of these surrogates, if they all rely on data, I think as an industry, we need to collect good data that we're all able to play with, that's meaningful and relevant, to encourage us to get these skills so that we can then discover and innovate. Again, building that trunk together. And actually, this is pretty much the end of this pitch. I just wanted to say, in review, this surrogate modeling workflow, right? There's a lot of machine learning out there, more than we have time to go through. I'm focusing on one very specific algorithm type, a regressor, a universal function approximator, a surrogate model that I see as an opportunity to take any parametric model that we use all the time in design, to take that and translate it into an instantaneous predictor that not only can do our current working faster, right, to analyze a model instantly, but more importantly, to map the design challenge so that we can then support our design process with a larger understanding of the challenge that we face. And that our current toolkit can't do, and I think surrogates can. So yeah, if you can model anything parametrically and you can spin up a bunch of data, you can train a surrogate and then deploy it this way. So I hope this is a useful and practical application of machine learning for the industry.
Yeah, I got a couple of questions here, and one you're probably seeing these, so you're probably answering them in your thoughts. But that was one of them. Was what can we do to kind of like build these? Can there be shared models? Can we access them from each other? Well, I'm going to ask the question that I'm sure is going to come up, but where can people actually access either the PowerPoint or the code on GitHub? Are you sharing any of this? I mean, everyone, it's already on YouTube, so people can like click through real slow and type it up themselves. But is that going to be available? Can we get that on Slack? And I know
Yeah,
I'm
that's a
putting him
great
on the
question.
spot, guys.
I hadn't gotten that far.
No worries.
But yeah, no, I'm happy to share the presentation. I don't know the best format. Is there a way through Your Desk University, the
Yeah, the
website, to
best,
share?
and that actually kind of
Yeah.
highlights. We have a Slack channel, and we have one more episode for this trimester or semester. So if you are wanting to know when we go live next semester, there's 3 ways to do that. 1, you can find me on Twitter at Tim and Hazel. 2, you or hashtag yourdeskuniversity.com, Your Desk University on Twitter. 2, on Slack. So if you go to our website, yourdeskuniversity.com, and you go to the bottom, there's a join us on Slack, and Leland, you can post the PowerPoint on there so people can find it.
Cool.
Then there was one more way to find us. Oh, and then hit the subscribe and bell. I know that sounds silly, but if you hit the bell, you'll get notified when another one of these comes up. So when the next semester comes, you want to know about it. That's the best way to do that. All right, back to you.
I wanted to just mention, you're talking about
Sure.
sharing this stuff, because I mentioned the idea of sharing data. I'm actually in the process of working on a grant with Oak Ridge National Labs to develop sort of super massive design spaces. But the goal of this project is to release it publicly for that purpose. So over the next year or so, we'll be developing a lot of energy modeling data that I really hope to get in everyone's hands. And I know there's other people talking about this. I think Kaggle is probably a great place to post the raw data. So if there's anyone listening who has their data sets, I know I've got that one design space with Dr. Mistrick. I've been meaning to get it up there. Maybe this is one more opportunity to actually go the full mile and get that done.
Yeah, and there's been some really cool, interesting open source stuff. I'm not gonna kind of spoil it, but I know Chris has done stuff with other groups, open source, in order to get their models better. And I'm imagining machine learning is another area where they're growing as well. All right, I'm gonna pause. You're seeing these too. By the way, you asked if the Rhino team was here. Bob McNeil himself is in the house. So
Thank you.
Well done. And thank you for watching. I found out actually my CEO watches this as well. How crazy is that and fun? All right. Have you done an analysis? You talked about the 60,000. What to you has been enough or good enough for simulating data as far as like quantity, amount of data?
Oh, that's entirely based on the design space you're trying to simulate in your question, right? I've found that anything less than 3 parameters, just do it manually. It's really not enough. Most design problems I'll face for an actual project. I can get it down to 5 or 6 parameters. Anything more than that, and you're out of the 1,000 simulation run, which is sort of feasible. You very quickly run into the curse of dimensionality, right? And it starts to explode. And I think for your universal design space, you're honestly looking at even the 60,000 we have doesn't include everything we'd like to look at. You very quickly get up to the 6, 7 figure mark.
Hmm. Yeah,
Yeah.
I mean, you need when you start getting to that totally makes sense. Great.
And there's an art to framing that.
So you talked a little bit. I want to come back to the design space problem that you talked about, and I think this will answer a couple of the questions that are going out there. But and you talked about universal modeling of something, but it sounded like in the projects where you've done this, which by the way, great job, great work. I really appreciate you sharing this. You've looked at a specific design problem. So people said like, hey, this is what my facade is kind of looking like. This is the direction, and then you could like look at that specific design problem and that specific geographic area, thus limiting those extra features in order to create this design problem. What do you
Exactly.
think? What do you think it takes to get to a larger, more universal design problem? And I'm hoping this hits on some of those questions that are coming out as well.
What does it take to get there?
To get to like the
A
next
lot.
level where it actually is a universal design problem that can actually help you, in any geographic area. I mean, is it just more runs?
Yeah, in short, yeah, it's more runs because you think about you have more parameters to answer that. So I mentioned the idea of variables that you're interested in, the design questions that you have to make, or design decisions you have to make, and then there are other things that are more about filtering down to I'm in this region or I'm in this type of building for energy modeling. So in order for it to be universal, you need to have enough filtering parameters to ensure that your design lives within the space you've simulated. And so there's a lot of extra parameters to widen the space to include any possible project. And then you need it to be relevant enough. So you need to capture the common design questions that you might have. And a lot of this is like we're going to assume an 80/20, right? We want to hit 80% of the projects. We don't care about the 20% weird ones. And that I think there's a lot of work to be done of what questions can be effectively captured in
Hmm.
as few parameters as possible. And that's
Yeah.
it's a new way of thinking and a new way of modeling our design challenges.
Yeah.
But there's a lot of low hanging fruit out there.
Tiny request, can you stop sharing? I think your internet speeds just dropped just a little bit, but I think we should be fine once you do that. Um, I wanted to ask, wanted to go a little bit of a different direction in how you got here. So I saw on LinkedIn you were doing a collective study machine learning study group recently, which I thought was really cool. A good way to engage other people, and actually something I was like, wow, maybe your desk university wanted to do a workshop like that. If you're interested in doing something like that, kind of a study series with someone, we did one on Python. But if you are interested, reach out to us. Let us know you want to participate in something like that on a particular topic, any topic. Now back to the idea of how could somebody, so kind of, I guess let's just focus on your story. How did you get here? And then what key pieces of your learning do you think were important to get to where you're at? And then what's next? So kind of the
Mm,
past, how'd you get here? And then what do you think the next is for you as far as the learning in this particular
learning.
space?
Yeah, well, I would say a big part just came from a need to solve problems and recognizing the power of some of the new tech. So when I stumbled into Grasshopper, for example, I was like, wow, this is a better way of working. So a lot of it was just having problems that needed to be solved and being curious enough and convinced by the current methods to say, hey, I think there's a better way. Let's do it. So you gotta be constantly learning.
Mm-hmm.
As far as the stuff I'm showing today, I actually saw somebody talk about machine learning at a conference several years ago, and he said, "Hey, I took this Udacity course," and I just went and took that, and that was really, really helpful. There's so much out here I wasn't taught in school, so I would strongly encourage you: don't expect to learn all of the stuff you need to learn at work. I know that sucks. You'd like to, but there's a lot of things out here to learn. In particular, data science. So I took data science first, then I took machine learning, and I got a kind of a good sense. But then I was able to apply it at work. Um, as far as learning goes, I think Grasshopper can get you quite far. But I have, as much as I love Grasshopper, I do think there are certain applications it is a dream it's made for, and there are other things that
Mm-hmm.
it's really not. And you're going to need to learn Python or C sharp, proper coding. I know that's a gap I have. I'd really like to learn more about actual software development rather than
Yeah.
just writing Python like I write my Grasshopper scripts. Uh,
And I appreciate you saying like you're not an expert on Python, and that's not what today's workshop is. We've had other one of those in the past. I do think Python is key, right? With the space that machine learning is growing right now, Python is key. We see that in the chat right now. Definitely super important. Let's see. Looking here for questions. I've got a couple of minutes, guys. If you have questions, toss them in the chat. Otherwise, we'll go. Let's see here. Just looking. You can look through too if I missed one maybe that you thought should be covered.
Oh, so something I see a question here that's saying, what's the best route to achieve these kind of methodology in AI or ML? I personally mentioned at the beginning, we want to make this, we want to demystify machine learning. I think it's really important. I know we even use the buzzwords to get people to attend this. I think it's important that we start breaking them down from these big topics, or even talking about supervised and unsupervised. Let's talk about them as tools. What do they do? What can they do for us? Let's talk about classification. Let's talk about what regressors, surrogate models, right? Let's kind of break it down into the smaller chunks. I think that might help us all see how they can be used better.
And I do think that's important. And there you go. You brought up that question again. Was this buzzwords? If this was buzzwordsy, if it was all just buzzwords made up, hit the down like button, which I don't even know that anyone ever uses. If you liked it, hit the up, say something in the chat. Let us know, because we really want to give you, better content. So let us know. Did we hit the mark that we set for ourselves? So with that, Leland, thank you so much for the time that you've given us and for presenting and sharing all this. I think, I know, yeah, I definitely appreciate it. And we will see the rest of you guys later, if I can find the quit here. We are good, but...